Swayam Prabha. Digital India. Educated India.
A line of longitude like this, all of equal area. The question is, does this form a tiling of the sphere or not? Because in this problem, P is equal to 2, two-sided, and Q could be any value greater than or equal to 3. The question is it tiling? And I said that's not really an honest tiling. The reason I said that was because, yes, in a sense it is a tiling. It's a regular tiling, all right, I agree. But the point is that you can always take this surface here, the sphere, and project it onto a plane. It's called stereographic projection. And the rule of the game is the following. You start with a sphere, unit sphere, and this is the origin. The center of the sphere is the origin. This is the surface of the sphere. The equator is like this. Now consider the plane of the equator. So there's this whole thing. The big plane, infinite plane, the equatorial plane. Then any point on the sphere can be mapped uniquely to a point on the plane by drawing a line from the North Pole to that point and extending it. So here's the North Pole. You draw a line like this, it intersects the sphere at this point, and that corresponds to this point on the plane. Okay. The North Pole is mapped to the point at infinity. All the points at infinity on this plane are mapped onto a single point here. The South Pole is mapped onto a line from the North Pole to the South Pole right through the sphere will go and hit the center of the origin here. So the origin of the plane is the South Pole, and infinity on the plane is the North Pole. Then if you look at this kind of tiling, or what you've done is to take the plane, and on the plane you've done this. At any arbitrary angle here, less than 360 degrees, less than 180 degrees, you have rays from the origin. So the line of longitude will go from this point to this point. That corresponds to a straight line through the origin going all the way to infinity in the plane. So in a sense, this is a tiling of the plane, but it's not an honest tiling because they consist of equilateral triangles in which each side is infinity. So that's the reason I objected to it to be a tiling. Okay. But yes, you can extend it and say the idea of notion of tiling and say that it satisfies all the requirements of regular tiling. I agree with that. So that was a bit of semantics. Now what I want to do now is to show you how we got a very important formula in mathematics, how we got Stirling's approximation. So our target is to define, is to show this relation, n factorial, n to the power n, e to the minus n, square root of 2 pi n, times corrections which I'm not going to write down here. So we want to derive this formula explicitly. For that we need to know what's something called a Gaussian integral. Are you familiar with Gaussian integrals? Do you know what a Gaussian is? I don't mean this program that was discussed yesterday. But do you know what a Gaussian function is? This function, e to the power minus x squared, is called a Gaussian. It's called a Gaussian function, where x is a real variable running from minus infinity to infinity. And we can plot this function very easily. It's a symmetric function of x. It dies down very rapidly as x goes to plus or minus infinity. And it's the classic bell curve. It's got a peak at the origin at x equal to 0. This is what it looks like. It's called a Gaussian. And this function has a very weird property. There is no function, a simple function, whose derivative this function is. So it doesn't have an antiderivative. It doesn't have an indefinite integral. We're going to define a definite integral involving the Gaussian, but it doesn't have an indefinite integral. That is, there is no function whose derivative this function is, except a trivial one which I can write down in terms of this function itself. If you know how to differentiate under the integral sign. Has this formula been taught to you by anybody? How do you differentiate under the integral sign? I mean, by this I mean the following. If you have a function of x defined as, in terms of another variable u, du g of x comma u, from a limit which is, say, a of x to b of x. You have two variables x and u, let's take them to be real variables to start, and I define a function f of x which is the integral from some limit, lower limit in u, which is a of x, a function of x, b of x on top, and then a function of two variables, g of x comma u. And the question asked is, what is df by df? Very useful formula, by the way. This is called differentiation under the integral sign. What is this equal to? If I draw it in pictures, suppose g of x comma u looks like this. Some function like this. And this is b of x. This thing is a of x. This is the u axis. And the function looks like this, in this range, from a of x to b of x. The way I find the derivative of this function, f of x, is to take f of x plus dx minus f of x divided by dx and take the limit. That's the definition. If this is f of g of x comma u, then what happens to g of x plus dx comma u? It would look like this, slightly shifted. Possibly this is the new b of x plus dx and this is the new a of x plus dx. And I need the difference between these two fellows because the area under the curve is the definite integral. There are three contributions. One coming from the fact that g itself has x dependence, so there's a derivative in which u is kept constant. Then there's this limit here which has got to be differentiated and this limit has got to be differentiated, right? So if you put that in, out emerges a very useful formula, which is the following formula for f of x. Integral from a of x to b of x and du delta g of x comma u over delta x. This is the partial derivative. It says treat u as a constant and differentiate with respect to x. The explicit dependence on x inside this function g of x comma u. But then there is also a contribution from the fact that the limit here has shifted and the limit here has shifted. This is the upper limit. So what happens is, the way I defined it was with an upper limit b plus db over dx, d of x over d of x, g of b of x, x comma u, x comma b of x. That's an extra contribution. Minus so that's called the formula for differentiation under the integral sign. A very useful formula in calculus which is worth memorizing. Three contributions, one from the explicit dependence of g on x, second contribution from the fact that the upper limit depends on x, and the third contribution from the lower limit depends on x. And this appears with a minus sign here. This is the same minus sign that appears when you do something like this. If you have
how do we understand intuitively that this formula will give you df by dx?
put that in and ask what's the difference between these two areas now. This comes because the lower limit is fuzzy, it's shifted, and this comes because the upper limit is shifted. The question is, why is there a minus sign in between? That's the same as the theorem of in vector calculus about Gauss's theorem about the flux. This minus sign is exactly the same thing as the fundamental theorem of calculus. So if you have, for instance, an integral from a to b of d phi over dx, this is equal to phi of b minus phi of a. the same minus. Okay. This interval has two boundary points, left and lower boundary and the upper boundary, and the flux is outwards. So that's where the minus sign comes from, and this is very useful. So now consider this function, integral from some lower limit which you can take to be minus infinity without loss of generality because it doesn't matter, to x e to the minus u squared du. And I ask if phi of x is equal to this, what is d phi over dx? Using that formula, what would you say? There is no, what's inside the integrand is this function is g of x comma u, but there's no x dependence. So this term would not contribute. The upper limit does have x dependence. So what would it contribute? Dx over dx is 1, right? So this part becomes 1. And g of, there's no x dependence, b of x is x itself. E to the minus x squared. And the lower limit is constant, so its derivative is 0, right? So that's the best I can do with e to the minus x squared. No other trick will help me integrate it. And yet we want to find what's the area under this curve. Okay. So that's called a Gaussian integral. So I'm going to show you what the value of this is and how to do it. It requires a trick, and the trick was discovered by Poisson way back in 1815 or something like that. He is responsible for this particular trick. It's a cute trick. His argument was as follows. Are you familiar with plane polar coordinates? Polar coordinates, you put x is r cos theta, y is r sin theta, and do that. Right? So you can describe a point on the plane either in Cartesian coordinates or in plane polar coordinates. Right? Every point can be done. There's a connection between the two, but you can ask the following. Given the xy plane, you can ask, how do I calculate areas in this plane? If I have, for instance, a function which looks like this, a region which looks like this, how do I calculate the area of this area inside the bound, the closed figure? What do I do? I put a mesh on this figure and add the area of all the meshes, right? So I put a grid on it. And if this area is A, then I would say A equal to integral dx, integral dy over this function, whatever it was. So I calculated by counting all the grid points and finding out what the area of those guys is. The area of each infinitesimal element is dx dy. Okay. But if I were to write this in polar coordinates, what would happen? Remember that these lines, horizontal lines, correspond to y equal to constant. And the vertical lines correspond to x equal to constant. Right? And that's how I form my grid. What will the grid look like in polar coordinates? Yeah, what do the curves theta equal to r equal to constant look like? So you have a set of concentric circles. These are all r equal to constant, r equal to a bigger value, etc. And what does theta equal to constant look like? Theta equal to 30 degrees, for instance, would be a radial line. And this is 180 plus 30 degrees. It would look like this. These would be the grid points, right? So let me magnify this particular grid, this particular mesh, this particular infinitesimal area. Okay. If it's at r comma theta, this is theta, this angle is theta. What would this little infinitesimal element look like? somewhere arbitrary at this point, for instance. This let's focus on this guy here. This is R. This is R plus dr. And what is this arc equal to? So let me magnify that. It's a piece looks like this. This is dr. Goes to the origin, that's r. So that is the point. What is this equal to? This is r times d theta. So what is this equal to? It's r plus dr times the same d theta. But dr d theta is of second order infinitesimal and you neglect that. Right? So what's the area of this guy? R dr d theta. R d theta times dr, right? So you could also write the surface integral either as integral dx dy, this is the area element, dx dy, or dr r dr d theta. And if I want to integrate over the whole plane, x runs from minus infinity to infinity, y runs from minus infinity to infinity. What does r run over? 0 to infinity, because r is the magnitude of the distance from the origin, 0 to infinity. And theta? 0 to 2 pi, that covers the entire thing, right? So I can replace an integral in dx dy by an integral over r and theta. Okay? So Poisson's clever trick was the following. He said, I want to calculate the following integral, and here's how he explained it. We want to calculate the integral I equal to integral e to the minus x squared dx minus infinity to infinity. This is the fundamental Gaussian integral. It represents geometrically, it represents the area under this bell curve. And this integral converges. You're supposed to take minus r to capital, minus x to minus L to plus capital L, and take the limit as L goes to infinity. And it's a finite answer. We're trying to find out what this answer is. He said, let's not do this integral, because integration by parts will not work here, as you can easily convince yourself, and there's no other trick to do this. He said, let's not consider the integral itself, but the square of this integral. So he said, let's also write this equal to integral minus infinity to infinity e to the minus y squared dy. Y is just an integration variable. Because he was Poisson. To do the integral, you'll see in a minute what happens, right? What happens if you multiply these two integrals together? It's just the product of these two integrals. So minus infinity to infinity, integral minus infinity to infinity dx dy. So e to the minus x squared plus y squared. Okay? That's the square of the integral. I shouldn't write dx once again. I should write dx once and dy once, because they are summation indices. They are integration variables. You can't use it more than once. If I want to write the cube of this integral, I'll have to use another symbol, z for instance, right, as the product of three integrals, etc. Can I write this in polar coordinates?
Yes, sir. Dx dy.
Look at what happens if I do that. I squared in polar coordinates becomes the integral from 0 to infinity dr. Let me write this dr right away next to the integral sign to remind myself that these are the limits of integration in r. Integral 0 to pi, 2 pi d theta multiplied by r, because remember that the volume element, the area element is r d theta dr. Very important to remember that. Multiplied by whatever this function is in polar coordinates. What is this equal to? E to the minus r squared. That's the Pythagoras theorem. X squared plus y squared is r squared. What is striking about this integral? Is there any theta dependence in the argument? You can do the theta integration immediately. 0 to 2 pi d theta. What's that equal to? 2 pi. It's just 2 pi. D theta is times 1. And 1 is integrated from 0 to 2 pi. It's just 2 pi. So this is 2 pi. Integral 0 to infinity dr r e to the minus r squared. R e to the minus r. Exactly. Crucial point. What do I do next? Do you think there's a hope of doing this integral? What should I do? Integration by parts won't get you anywhere because we don't know what to do with this. Yeah, can I change variables? Put u equal to r squared. No, then the limits of integration will get screwed up. You want it to go from 0 to infinity. So what is du? So I'll take this 2 in. 2r dr is du. So this is equal to pi times integral. What are the limits of integration? When r is 0, u is 0. When r is infinity, u is infinity. So it's 0 to infinity. This is du. That's e to the power minus. Now we can do this integral. What's integral e to the minus x? Minus e to the minus x, right? So what does this give you?
Pi into minus pi into e to the minus r square.
No, don't do r squared. Put the limits in first. So it's equal to minus pi minus 0 to infinity. What's that equal to?
E to the minus infinity 0, minus 1, so minus of minus pi, so pi.
Pi. That's the fundamental Gaussian integral. So we've succeeded in this. Therefore, it tells us that the fundamental Gaussian integral minus infinity to infinity dx e to the minus x squared equal to? No.
Oh, root pi.
Square root of pi because we found I squared. Okay. The most beautiful result. What happens if I shift this peak a little bit? What happens if I try to generalize it? Once you have this, you can do a whole slew of integrals. So I have a function like e to the minus x squared, the Gaussian function, for which I don't have an indefinite integral, but I can still do a definite integral from minus infinity to infinity and just square root of pi. What about this integral? A is any real number. What would you do now?
Since it's tending to like infinity or
What would this graph look like? Where A is any real number, what would positive or negative? We don't care.
Just shifted across the.
It just shifts to that point. So it's still like this. to this point A. Do you think the area under the curve is going to change? It's not. I put x minus a equal to u and dx is du. So I'm back to the Gaussian integral. It's also square root of pi. Independent of a. What about this integral? A is a constant, positive constant, so that remains a negative number and converges, otherwise it blows up. What is this integral equal to? How do you get that? Yeah, put ax squared equal to pi equal to u and do the differentiation again. So this is equal to root pi by a. What about this integral? Integral minus infinity to infinity dx e to the minus a x minus b the whole square. The shift here is harmless, doesn't do anything. It goes to Gaussian integral like e to the minus a u squared, which is root pi by a. So you can write that down. How about this? How about dx? What should I do now? A and b are real numbers and a is positive, so the integral converges. What trick will you use now? The number of tricks I have at my disposal is finite. I can shift the Gaussian, I can rescale the Gaussian. How do I get into that form?
But you just be into dx. That's still
Completing, somebody said completing squares? Yeah, that would be a good trick. Let's try that. What do I do next? What's the completion of squares? What do you get here? Plus? So you pull that out. So you get you got a shifted Gaussian, scaled, rescaled, but this factor b squared over 4a comes out. It's constants. Multiplied by the answer to the Gaussian integral. So you can do a whole family of integrals using this. Okay. It's a very sharply peaked function, and this function, general Gaussian looks like this. It's a probability distribution. It's called the Gaussian distribution or the normal distribution, and the distribution looks like this. The probability density looks like 1 over square root of 2 pi sigma squared e to the minus x minus mu whole squared over 2 sigma squared. This is called the normal distribution of a random variable x with 0 mean and variance 1, variance sigma squared. That's the notation for it in probability theory. This quantity mu is the mean, where there should be mu. And this quantity sigma squared is the variance. So roughly speaking, it's telling you that the probability distribution looks like this. This peak here is at mu, and this width here is proportional to square root of sigma squared, which is sigma. So this is called a standard deviation. Sigma squared is called the variance, with this 2 present here to cancel this, and mu is the mean. When mu is set equal to 0 and sigma squared is set equal to 1, you get the so-called standard normal distribution, Gaussian distribution. Very, very useful thing to remember. But back to Stirling, we want to find Stirling's formula. So we need the Gaussian integral. I'm going to argue like this. Notice one fact. The width of this curve, this full width at half maximum, is proportional to sigma. That's important to notice. And the peak occurs at the mean at x equal to mu. Now let's go back to our integral. The first thing I observe is that n factorial is equal to integral 0 to infinity du x to the power n. In fact, this is the reason why I want to define 0 factorial as 1. It comes from this family of integrals. It's easy to check by integration by parts that this is going to give you for n equal to a non-negative integer, integral x to the power n e to the minus u running from u equal to 0 to infinity is just n factorial. Easy to establish. Now I want to know what happens when n becomes very large. 10, 20, Avogadro's number, etc. What I observe is the following. If you look at the u plane, look at it as a function of u, the function x to the power n increases very rapidly like this. It's very flat here as n increases, and then it rapidly increases to infinity. E to the minus x on the other hand, e to the minus u on the other hand, oh, what have I done? Let's do x plane. Just one function x. So this is x to the power n. What does e to the minus x look like? It starts at 1 and then rapidly decreases like this. The product of the two, what will it look like? At 0, this function dominates because e to the minus x is e to the 0, which is 1, finite, but this x to the n is going to 0 quite rapidly. So the product is 0. And at infinity, which dominates, this function or e to the minus x? E power minus x goes to 0 faster than any power of x, any reciprocal power of x. So this dominates at infinity, this dominates at 0. What does the product look like? What can it possibly look like?
Why is e to the minus x approaching 0 faster than any point?
Multiply e to the minus x by x to the n, where n is any positive integer, and ask what happens when x goes to infinity. Take the limit, use L'Hopital's theorem. So 0 times infinity, use L'Hopital's theorem, and e to the minus x dominates. Okay? Shortcut in calculus. The exponential dominates over the power, and the power dominates over the logarithm. So that's the hierarchy. So the product of the two will necessarily look like something like this. We peak somewhere in between. We need to know where this peak is going to be. It goes to 0 at both ends, but there's a peak somewhere in between. We need to know where this peak is going to be. What do you think it is? I should rewrite this in such a form that I can recognize where the peak is. So let me do that.
Sir, what reason do we have to believe that there's a graph in these symmetry?
It's not symmetric. It's not symmetric at all. As n gets larger and larger, I'll show you very shortly that this peak gets narrower and narrower and higher and higher. Okay. But this is what I expect. But I need to prove it. Right? So let me write this x to the power n e to the n log x. All logs are to natural base e, right? X to the power n is e to the n log x by definition. So what I have, this n factorial is equal to integral 0 to infinity dx e to the power n log x minus x in the exponent. In this function, actually this exponent is going to, there's got a minus sign here, this is always going to be smaller. So let's write it as e to the minus, and let's leave it like that. So I've written it in the form dx e to the power of function of x here. Okay. When is this going to be largest? At some extremum, right? How do I find the extremum of this function? First derivative should be 0, second derivative should be either positive or negative depending on whether you want a maximum or a minimum. So let's put f of x equal to n log x minus x. What is f prime of x? N over x minus 1. And when is it 0? When x equal to n. So for any given fixed n, the maximum occurs at x equal to n. The peak occurs at x equal to 1. There's only one peak, there's only one maximum. What is f double prime of x?
Minus n into n. Minus n by x squared.
And so on. Now let me do a Taylor expansion of this function about x equal to the maximum. Are you familiar with Taylor's theorem? So I'm going to write f of x as equal to f of n plus x minus n f prime of n plus x minus n the whole squared over 2 factorial f double prime of n plus dot dot dot. As I get closer to x equal to n, the higher terms get smaller and smaller. This function looks, the shape is such that most of the area is concentrated near x equal to n. So x minus n is going to be small. What's that equal to now? If I put it in. I know what f of x is. It's this guy. N log x minus x. What is f of n? What's f prime of n? We already found it. Right? F prime of x is n over x minus 1. So f prime of n is 0. We are expanding about x equal to n. So it's 0. What is f double prime? Alright, so let's put that in here and write n factorial equal to integral. Pardon me? I have e to the power f of x, and I see that f of x is dominated by its behavior near the maximum, near x equal to n. So I'm going to do a Taylor expansion about the point x equal to n. So the first term is just f of n. So this is 0 to infinity dx e to the power n log n minus n. That's f of n. The first derivative term is 0. The next term is x minus n, the whole squared over 2 factorial f double prime of n. What's f double prime of n? Minus 1 over n. So there's a minus sign here. 1 over n. 2 factorial is the same as 2. Plus higher order terms. Now what these higher order terms will do, and you have to do a little bit of hard work here, to show that they are subdominant. You can write them as a power series. E to the power x, you write as 1 plus x plus whatever, you can take it down. There will be the corrections. So the leading term is just this. This requires a little bit of care. This is equal to, this by the way, this guy here is a constant, no dependence on x at all. So I can pull it out. What is e to the n log n? N power n.
Yeah.
What's e to the minus n? That comes out, e to the minus n. Integral from 0 to infinity dx e to the power minus x minus n the whole square over 2n into 1 plus corrections. This looks almost like a Gaussian integral, right? But the larger n gets, the further the peak shifts to the right and the narrower it gets. The relative thing, relative to the mean, the standard deviation is square root of n, divided by the mean is n, so it goes like 1 over square root of n, right? So geometrically, I have an integral which is essentially 0 everywhere except for a very sharp peak here. So I might as well take this peak and extend it all the way to infinity, to minus infinity. So that's the big step, which requires a little bit of rigorous justification, but take it from me that it's valid. N to the n, e to the minus n, integral minus infinity to infinity plus corrections to it. So I've extended the integral from minus infinity to infinity by adding stuff to it, but I should show that that's exponentially damped compared to what's retained on the board. That's where the corrections come from. Requires a little harder work. But this integral we know how to do. It's a Gaussian integral with peak at x equal to n, and this multiplicative factor a is 2n. So this is equal to this root 2 pi n comes from here and the Gaussian integral. Okay, that's Stirling's formula. Yeah.
So the fundamental assumption that you started off with was that you could write the n factorial as the integral of x to the power n
Yeah.
to the power e minus x.
Yes.
How do we know that assumption to be true?
Euler told us so. It's called the Euler integral.
And how did Euler know that to be true? Sir?
Because he was Euler. Actually, Euler did more. He found the extrapolation of the factorial itself. If you plot the factorial, plot n factorial, it rapidly increases, right? Here's 0. 0 factorial is taken to be 1. 1 factorial is 1. 2 factorial is 2. 3 factorial is 6. 4 factorial is 24. It's way up there. So it increases extremely rapidly. So Euler's question was, is there a function which interpolates between all these guys? This fashion. And he said, yes, there is. It's called the gamma function or the Euler integral. And that interpolates between these fellows with some restrictions and so on. And it looks like this. So the gamma of x was equal to n minus 1 factorial.
So does the factorial function overtake the exponential, or is the exponential still fast?
Overtake means it's going on to infinity or going to 0?
Yeah, to infinity. Which is dominant? Which is dominant?
Which is dominant in which are the two functions?
Factorial and exponential.
Factorial goes like n to the n e to the minus n. Right?
Yeah.
So it will be stronger because there's an n log n.
No, sir. Can you repeat once?
It increases. There's an n log n. It's n to the power n. Whereas the power will be just e to the power n. E is finite.
Right.
So n to the n will be dominant. So this gamma function looks like this. It goes to infinity at origin 0, and then it goes off like this. This is the point 1. This is the point 2. So this value is 1 at these 2 points. It's infinity at this point, and it interpolates between the factorials of the integers. This fashion. You can generalize this further and ask what happens to negative values of the integers, what happens to negative argument, what happens to complex argument, etc., etc. And the gamma function is well defined for complex argument. At all negative integers, including 0, it blows up.
Okay, is this okay? This is also my first.
Yeah. Does weird things. So it will have at all negative integers, including 0, it diverges at those points. All the functions you are dealing with, it's useful to think of them as functions not of a real argument but a complex argument. And the real case is just a special case. Because otherwise you end up with all sorts of paradoxes and things like that. For instance, if I ask you to plot n to the n, plot x to the power x, what would you say? I want to plot f of x to the power x for a real variable x. What would the graph be? Does it blow up as x goes to infinity? It does. And what can you say about negative values of x? It becomes complex, right? So you can't represent it on the real plane. What does it do at 0? 0 to the power 0, what should I do? How should I interpret 0 to the power 0? X to the x I write as e to the x log x. Now I let x go to 0. X log x, log 0 goes to minus infinity. X goes to 0. Which is stronger? Yeah, but which is stronger? X is stronger or log x is stronger? X is stronger. So x goes to 0, log x goes to minus infinity. 0 times infinity? 0. So e to the power 0 is 1. So this function starts at 1. The limit is 1. You have to specify the limits always, what order you have taken limits. Here I'm letting x go to 0 from the positive side. So it's 1. And then what does it do? Slope is negative. Eventually it's going to blow up on this side. But is it going to go down and blow up, or is it going to go up straight?
Go down and blow up.
It's going to go down and blow up, right?
Go down until 1 and then.
Yeah, some crazy thing like that, and then go up. Yeah, which we can figure out easily. You can find out where the minimum here is. It's at 1. Okay. Now the question is, what does it do on this side? Is it complex all the way?
How is the minimum at 1? At 1 it should come back to 1, right?
Yes. The minimum is in between 0 and 1, sorry. Yeah. What happens on the negative side? Find the slope of this function at x equal to 0. It's negative.
X into log x
So it's got to go down.
minus 1 or plus 1.
and find where the slope vanishes, which is the point between 0 and 1. What about negative values? It becomes complex, it becomes imaginary, in general complex, right? But I know what minus 1 to the power minus 1 is. What's minus 1 to the power minus 1? Minus 1. So there is a point here. That point belongs to this curve. What about minus 2 to the power minus 2? Plus 1/4. So there's a point here. Similarly, there's a point here, etc. So there's an infinite number of points at all the integers. They're all real values, right? They're isolated points, but they belong to this graph. That sounds weird, but actually you should interpret this thing as z to the power z, where z is a complex number. Then you need 4 dimensions to represent it, because z has got a real and imaginary part, and z to the z has a real and imaginary part. So I'll have surfaces, but in 4-dimensional space. And these are like balls which come and touch the real section at isolated points. So you're not seeing the rest of the animal because it's all in the complex. Okay. So complex analysis in some sense subsumes real analysis. It's useful to think of it that way, because then a lot of complications are avoided. That's the way it is actually. Then all trigonometric functions and hyperbolic functions are the same essentially, with different arguments. For example, cos I theta is equal to cos hyperbolic theta. Sin I theta is I sin hyperbolic theta, and so on. Trigonometric and hyperbolic functions are just analytic continuations of each other. There's only one function at the root of all this, and that's the exponential. You take its symmetric part, you get cos hyperbolic x. You take its antisymmetric part, you get sin hyperbolic x. And sin theta is the imaginary part of e to the I theta, and cos theta is the real part of e to the I theta, or the symmetric part of it. Etc. So think complex all the time. This complex analysis is very powerful. Okay, this is all I wanted to say. It's indeterminate, but when we ask for limits, it's got a limit. Now, if I write f of x is x to the power x, the mathematician would say 0 to the power 0 is indeterminate, not defined. I can define it as I please. But if I want limits, if I want continuity, I would define it as a limit of x to the power x as if it exists.
So, but limit is tending value only, right?
Yeah.
It's not exactly at 0. So do we say there's a hole at 0 and just...
Yeah, so I have to define my function in the following way. If I take the function sin x over x, at x equal to 0, it's indeterminate. I can define it as I please. But if I want continuity, I would define it as 1.
Yeah. Okay.
I define that function as the limit, if it exists.
So suppose in a hypothetical case 0 over 0 came up in another function, and it could assume that, and at that point the limit approaches a different value, 0 over 0 would take the value.
Yeah. And limits are something which you have to dictate. If you're doing physics, the math itself doesn't tell you what limits to take. If you have two variables a and b, or x and y for instance, x to the power y, if I look at this function, x and y are independent variables, say, and I want the function x to the power y. I want to know what it does at 0. It's completely arbitrary, right? If y were a function of x, I could see whether the limits exist and things like that. But if they're completely arbitrary functions, unrelated variables, then the value of this function will depend on whether you're going to x goes to 0 first or y goes to 0 first. So what I'm saying is this limit x goes to 0, limit y goes to 0. is not equal to, in general, not equal to limit x goes to 0, limit y goes to 0, x to the power 1. From the positive side. When I say goes to 0, I mean both positive side alone for both variables. What happens to this? If this guy remains positive and non-zero, and x goes to 0 first, the answer is 0. So in this case, you get 0 as the answer. But if you did this, you let y go to 0 first, it becomes 1. And then x goes to 0 doesn't change it. So if you have a double limit like this in a physical problem, the physics has to tell you what order of limits to take. The math doesn't tell you, it gives you ambiguous answers. Each completely consistent, but which one you choose depends on. It's just like when you have a physical problem, like you have a number satisfying, you have some variable satisfying a quadratic equation. If you have a physical requirement that that answer should be positive, you omit the negative root. The equation itself is got two roots, but you have to choose the root. So the roots would have less symmetry than the equation itself, right? If I give you an equation like x squared equal to 4, what are the roots? Plus or minus 2. Now, which one you choose would depend on the physical application of this whole thing, right? So the equation is invariant under x going to minus x. So the equation has a symmetry. Does the solution have a symmetry? The solution is 2 or minus 2, and under x goes to minus x, the solution 2 goes to minus 2 and minus 2 goes to 2. So what is the moral of the story? If the equation has a symmetry, individual solutions need not have that symmetry. In general, will not have that symmetry. But the group of solutions, the set of solutions will have that symmetry. So the solution space remains unchanged, but then there's interchange in between. You understood all of critical phenomena now. That's exactly what happens. So at the end of the day, it's the physics that dictates what the answer should be in every given case. Should we call it a day? Any quick question? I find it charming the way you say, students say, I have a doubt. Or as they say, I'm having one doubt. I joke always saying that you and I don't have doubts. Mahatma Gandhi, Vivekananda, these people had existential doubts, etc. You and I have questions to which there are even answers most of the time. We are ordinary people. You have a doubt or a question? Doubt I don't guarantee about clearing up.
Why did Hassan take I squared, sir? Why not I cube, I4?
Why not take?
I cube, sir, I to the power 4, I to the power
What about them?
Sir?
What about them?
Yes, sir. What was so special about I squared that he had to take I squared?
You're asking a question, what's special about complex numbers? Pairs of real numbers.
No. I think the question is when you were deriving the Gaussian integral.
Oh, okay.
When we derived the Gaussian integral, we squared it to find the answer, right? So
Yes.
we are asking why square it, not cube.
I could have cubed it and then I'd have to use a volume element in spherical polar coordinates. Just needless complication.
Yes.
Can do it, there's no harm. Needless complication. By the way, can you raise an imaginary power to an imaginary power and get a real number?
Yes,
Yes.
Very good. Okay.
Sir, this was one of our lunch discussions, at least for the board.
Okay.
Yes.
Here's a fun fact. Somebody talked about Fourier analysis in one of the projects. Who did the Fourier analysis? Somebody mentioned Fourier analysis. You people did Fourier analysis, right? So you have the Fourier transform of a function of a real variable. x, call it phi of k or something like that. You can ask what is the Fourier transform of the Fourier transform. Okay? And it turns out to be the parity operator. In other words, f of x goes to f of minus x at the end. Which implies that if you take the parity operator twice, you get the identity operator. If you change x to minus x successively, you get the identity.
You get the original.
So you do it 4 times, you get the original thing. Which says that the Fourier transform operator is the fourth root of unity in the operator sense. In the operator sense. And it's got practical applications in Fourier optics. Because a lens is essentially a Fourier transform. A thin lens is essentially a Fourier transform. So there are deep connections of this kind all over the place. So final word of advice, I don't like giving advice, but final word of advice. When you learn these things for the first time, it looks like they're all disjointed pieces of information. But that's not true. There are underlying deep connections. So what you should do is to try to find these correlations and remember it accordingly.
Sir, wait. I didn't get the part where you said a lens is a Fourier transform. Because
Now I'd have to tell you how to do Fourier optics, which is a mess. But a lens takes a given incident image and then object and makes it an image, right? There's a mapping.
yes, sir.
This mapping can be shown to be a Fourier transform.
But then if you put stack multiple lenses,
Yeah.
you wouldn't get the original, right?
Yes, yes, yes. You put 4 of them together, you would, in a certain sense. There are approximations and so on involved in this business. You can also ask what are the eigenvalues of the Fourier transform operator, namely under what conditions you take a function of x, you apply the Fourier transform operator on it, you get another function. The question is what are the eigenfunctions of the Fourier transform operator, under what conditions do you get the same function, essentially apart from constants. And the answer is Gaussian, for instance, is an eigenfunction of the Fourier transform operator. There's one more property of the Gaussian function, which has very important consequences. And the eigenfunctions themselves are the fourth roots of unity. What are the fourth roots of unity? What are the fourth? There are four fourth roots of unity.
There are four roots of unity.
Yeah. Yeah, start from 1. 1 is the root.
Minus one.
Go up counterclockwise. 1, I, minus 1, minus I. Right.
Okay.
Wait, within the Fourier transform has to
Bro, operator Mari.
okay.
And each of them is an eigenfunction of the Fourier. The corresponding eigenfunction is a solution to this eigenvalue problem. There are further connections. If you take the quantum mechanical simple harmonic oscillator, its energy eigenstates are eigenfunctions of the Fourier transform operator. The ground state is eigenfunction 1, the first excited state is eigenfunction minus I, and so on, etc. Every fourth state is an eigenfunction with eigenvalue 1, which has its own applications. Will you stop? I understand this anxiety to download everything possible, Lord. One thing I have to say is, which is probably a valuable piece of advice, is you have to, some of these subjects, which includes physics and mathematics, I don't know about the other subjects, you don't read these subjects, you work out these subjects. You need some basic background knowledge to do a problem, but you should challenge yourself by closing the book, putting it aside, and trying to work it out. Put pen to paper and work it out on your own. Whenever you get stuck, consult the book. Get unstuck, go back to closing the book and trying to do it on your own. So you have to understand your own way, in your own way, every single thing. Don't rest till you're satisfied that you've understood it. Okay? So people often come and ask me, what book should I read? You don't need anyone's permission to read any particular book, but it doesn't help. All the reading in the world doesn't help unless you do it on your own. After all, that's how you learned arithmetic in school. You did hundreds of sums. You added hundreds of numbers together. Practice makes. You need a lot of practice. Yes. The great physicist Enrico Fermi, one of the greatest physicists of the last century, used to do definite integrals before breakfast because he said he had to keep his mind sharp. He didn't have to do it. He had a Nobel Prize and much more. But he said exercise is needed. Taste differ. He chose definite integrals, but he did many other things too. So thank you very much.
Swayam Prabha. Digital India. Educated India.